Tonight's guest speaker is the current director of the E.A. Milne Centre for Astrophysics at the University of Hull. This is a world-leading research institute and regional education hub. An education hub that has, through its various outreach platforms, touched over 3 million people in the last few years. With skills and expertise in astrophysics, space, cosmology, dark matter, stellar astrophysics, galaxy evolution, chemical evolution of galaxies, and how to find aliens. Our speaker is amongst this country's most influential scientists, with several hundred publications and many thousands of citations from peer reviews. With his outstanding work in determining the expansion rate of the universe while working with the Hubble Space Telescope, tonight's speaker and his team were awarded the Gruber Prize in Cosmology. Tonight's speaker places great emphasis on delivering public outreach to schools, colleges, and societies such as ours, and as a result has received several awards. And it's thanks to the efforts of our guest speaker that the number of female students entering physics at the University of Hull has more than doubled in recent times. So, here for you tonight, preparing you for how the universe will end, please welcome Professor Brad Gibson.
Wow, thank you for that. I shall endeavor to live up to that introduction. If my wife was here, she'd be just rolling her eyes. Oh my God. I shall do my best. Okay, I'm going to share my screen with you now, and you can let me know. Can you see that okay?
That's fine, yep.
Yeah, that's great.
Okay, so this one for me it's a little bit outside of my area of expertise. Most of my work, and most, I guess, the traditional astronomers that I know in the field have a tendency to look backwards in time. You know, we look back over the cosmos, whether we look back in time, just a short period of time to nearby galaxies, or a little bit further in time to further back in the cosmos, all the way back to cosmic microwave background. We have that tendency to focus on what has happened and how we've gotten from the Big Bang to where we are today. And I'll give a little whirlwind tour of that to set things up. But I did start getting more questions about what is the fate of the universe? Where are we heading? So I started to dig around a little bit and try to learn a little bit about something that, again, is outside of my area of expertise. And I've really enjoyed learning this. And for me, it has been a learning experience. And hopefully you'll pick up a few things along the way that you hadn't thought of before or didn't realize were coming our way between now and the end of the universe. As was noted, I'm at the University of Hull, and I'm the director of here at the university. The astrophysics research is embedded within the E.A. Milne Centre for Astrophysics. And apologies for those who may have seen this already, but it is just sort of a reminder that E.A. Milne, the namesake of our center, is not A.A. Milne, the creator of Winnie the Pooh and Christopher Robin, despite the surnames in common. They do have some very interesting overlap in the first half of the 20th century. But Arthur Milne, our namesake, was born and raised in Hull. When I moved my group here, I guess it's coming up on 6 years now that I relocated to Hull. The first thing I did was Google famous people from Hull. The Wikipedia page is very brief. There's not a lot of entries for that one. But in amongst that list of a handful of people from Hull was the name that I recognize, Arthur Milne. I remember from my days of taking my cosmology course at university back in Canada. I had no idea he was from Hull, and I have been very fortunate to link up with Arthur's daughter and grandchildren and extended family in the establishment of the center. As I was saying, if you looked at Arthur's Wikipedia page, you will see things about his work in, he's a contemporary of Einstein. They were good friends. He had his own version of what cosmology was. It was very much grounded in sort of the real world in which we live, where classical mechanics applies rather than the theories of general and special relativity. So he had his own version of what the universe was and how to describe it mathematically. It's elegant, beautiful mathematics. It's entirely incorrect, but it's beautiful, elegant mathematics. It is one of the solutions to Einstein's equation, but it is not the correct representation of our universe. He also did a lot of work on stellar atmospheres and how energy gets from the center of stars to the outskirts of stars. But if you do look at his Wikipedia page, you'll find there's more about his work in designing anti-aircraft gunnery technology in World War I, where he was seconded to Portsmouth, the HMS Excellence, where he and a group of astrophysicists took their knowledge of stellar atmospheres and applied it to the Earth's atmosphere and designing what is called echolocation. You know, World War I was that first war where you had to worry about things in 3 dimensions rather than just what's in 2 dimensions. You had to worry about zeppelins and planes coming in behind, you know, thick fog and thick cloud cover. And so using kind of triangulation by sound, he designed this echolocation technique that was used to feed information very quickly to those on the ground to optimize where they should be pointing their weapons. Let's see if I've got this button working. There we go. As I say, the center's been around for just a little over 5 years now. We had the opening here at the university. It was more or less the last time I wore a tie over here. But yeah, lurking at the very back is the commander of the Royal Navy, who came up from Portsmouth in sort of acknowledgement and recognition of the important role he played in World War I and again in World War II when he came back again and worked with the Navy in air defense technology. And this is Arthur's daughter, Meg, who played a pivotal role in the establishment of the center and the use of the name. And I'm just giving a little bit of context. Some of you may have seen this before if you've seen any of my previous talks, but for those who haven't, just to give some context to the group, since we are, I think, probably the newest astrophysics research group in the country, I think. And it's apropos of nothing. This is my lovely wife, Kate, who's a physics teacher here just north of Hull in Beverly. We have been very fortunate, as was noted in the introduction, a lot of our work outside of the teaching and the research that we do, which I'll come back to momentarily, a lot of the work that we have done has been in trying to widen participation and improve diversity. We've been fortunate to link up with a few astronauts that you may recognize there. Helen Sharman, Steve Swanson, Michael Foale are all honorary fellows of the center, and they're not there just because of their names, but they're there because they have a similar philosophy and ethos in terms of widening participation and taking the science subjects into schools and the next generation. So I've been fortunate to work alongside them and doing various school visits. This is some of our students here. And I'll just note in passing, because I'll mention it right again at the end. On the left is Emily Shelton, who's from Mansfield. We're fortunate to poach her away and as one of our top postgraduate students now working on our master's project. This is not one of our students. This is my daughter having a chat with Helen Sharman, the country's first astronaut. We do a lot of schools work and outreach with the public. We do about 100 events per year. If you include all the digital contacts, we're up to about 3 million people that we've interacted with in the last sort of 5.5 years or so. And this is, I'm not naive. The university didn't invest in the establishment of the Milne Centre because they had any great passion for astrophysics, but they do see the value, as you do as well, of using a visual science like astronomy as a way to engage and excite the next generation of scientists and engineers and mathematicians. Space and dinosaurs, that's how we reach the kids. And we play our part in that and embrace that role, that responsibility that we have in taking these science subjects into the region. And as noted as well, just in passing, when I first got here, about 10% of our first year cohort were women in physics. There's lots of reasons for that, and you can give an entire talk just on different initiatives that are in place to try to widen participation and diversity. Our focus in the first couple of years has been in gender diversity, although this is certainly just the tip of the iceberg in terms of diversity. And I've been very fortunate to have a number of, at the time, undergraduates who were like-minded in terms of that passion to try to improve our diversity, our demographics. And over the last few years, through various schemes that we run, we've been able to go from sort of that 10% first year students being women to 26%, 28% now. So we've not quite tripled, but certainly more than doubled the number of women entering physics. So more than probably the research and things that we do, this is probably the thing that I take the greatest pride in having a small part in, although largely it's been driven by these students and the sort of the next generation of undergraduates who picked up the mantle from these students to continue on with this changing face of physics campaign. And just one last thing before I leap into the talk. Again, as was noted in the intro, we cover everything from within the center here. There's 30 staff and postgraduate students spanning everything from solar physics, the origin of the chemical elements, through to the largest scale structures in the universe. Probably, I don't know, 2/3 of our effort right now is based around theory and computation, the other third being more the traditional observational approach. And again, one of the reasons why I moved my group here a few years ago was the university did a parallel investment in high performance computing. So we're very spoiled in having access to one of the country's most powerful facilities, particularly one of the most powerful facilities owned by a single university. And it's allowed us to undertake a lot of really exciting projects that I'll touch on right towards the very end. We also maintain a share of facility in Cambridge called Cosmos, which is the National Cosmology Supercomputer. Stephen, I'll recognize Stephen Hawking. Stephen and I have a grant, despite his passing, we have a grant that maintains the facility at Cosmos, and as part of that partnership, we maintain our access. So that supplements what we have here on campus, which is the facility Viper that you can see noted there in the text on the side. So that is just, again, to give you a little bit of context, since many of you will not have heard of the Milne Centre and what it is that we do there, and how we maybe differentiate ourselves a little bit with some of the other astrophysics research groups that are out there. So now to leap into the topic of the evening. And as I said right at the very beginning, rather than leaping in straight away and starting moving forward in time to see how the universe is going to end, just take a couple minutes to explain how we got to where we are right now and what we know about the universe right now before I start that moving forward in time. So if you do a Google search of, I think, cosmology, I can't remember the exact terms I use. This is actually the most used image in extragalactic astronomy talks that NASA put forward, and it encapsulates sort of the history of the universe in a single cartoon. From on the left, that the very beginning, where there's an enormous, where you're maybe more in the mathematical regime than the astronomy regime, elegant, beautiful mathematics that describe that very first phase, that tiny fraction of a second, just as the Big Bang is starting. Prior to that, you're really into the realm of mathematics. But our story starts with this almost effectively a singularity with nothing but primordial quantum fluctuations that are ultimately going to be the seeds that are responsible for the galaxies that we see around us today on the right. And we start off with a very rapid phase of inflation where the universe expands very, very rapidly, inflates very, very, very rapidly. It's during that phase, those first, in the first few minutes of that phase is when the hydrogen and the helium that are the ultimate seeds for all the other chemical elements that come later are formed. The universe is very hot, very, very hot, very, very dense. And it is so hot that the the building blocks that we're going to be using later, the hydrogen and helium, those are the elements, that really the only elements that are around at that point in time. If you think about, cast your mind back to what is hydrogen? It's, well, 90% of the atoms in the universe are hydrogen. Hydrogen is a very, very simple chemical element. It is one charged particle, a proton, and one positive charged particle and one negatively charged particle, an electron. And at that point in time, the universe is so hot that the electron, even though it wants to stick onto the proton and be what we call neutral, the electrons all get stripped off because the universe is so hot and it's so dense. So all of the electrons get pulled off of the hydrogen and the helium, and you have this thick fog, this thick sea of electrons. And the Big Bang, the energy associated with the Big Bang, it generates photons, just like the sun creates photons that we observe with our telescopes today. The Big Bang creates an enormous amount of energy, heat energy, and photons get released. But because the universe is so hot and so dense and it's filled with this fog of electrons, those photons can't actually move very far. They sort of just keep bouncing around inside of this fog. So even if you could go back in time that far and find yourself in that fog, you wouldn't have really anything to see because the energy from the Big Bang can't actually move. It just bounces around. It doesn't really get anywhere. Now, that all the while, for the next few 100,000 years, the universe is continuing to inflate very, very, very rapidly. And as it gets bigger and bigger and bigger, it's getting cooler and cooler and cooler. And eventually it gets cool enough that that sea of electrons that are floating around, blocking the Big Bang's energy from moving very far, those electrons recombine back onto the hydrogen and the helium. And that lifts the veil, the fog that has stopped the Big Bang's energy from moving very far. And then it's able to freely stream. And we see that today in the form of cosmic microwave background radiation, photons that are left over from the Big Bang. They're surrounding us today. They're very, very low energy, very, very cool temperature-wise. But if you took sort of took a little box that was a 1 centimeter on a side, right now in front of you, there's about 300 photons from the Big Bang that are going through that 1 cubic centimeter. Now you can compare that with how many photons are from the sun. I had to look this one up. It's about 3 million photons from the sun in the same 1 cubic centimeter. So what that means is 1 in 10,000 of the photons that are around you today are actually left over from the Big Bang, these cosmic microwave background photons. And as you look from point to point to point to point on the sky, which is what you're seeing in this color-coded map here, those colors correspond to slightly different temperatures. Almost all of the photons from the Big Bang have a temperature of about just a little over 2.5 degrees above absolute zero, say minus 270 degrees or so in Celsius. And those different colors that you see are subtle little temperature differences. So the blue regions might be 2.6999 degrees, and the red regions might be 2.70001 degree. And so we stretch the color table to show those different temperatures. So it looks like there's great differences, but there's subtle temperature differences, which correspond to subtle density distributions that are left over from those quantum fluctuations at the very beginning. Those are the seeds for the galaxies that we see today. And this is really as far back in time as we can look with our telescopes, back to a few 100,000 years after the Big Bang, where we see this lifting of the veil and the energy left over from the Big Bang. But encoded in those subtle little temperature differences and the way that mottled pattern is spread across the sky tells you an enormous amount about our universe today. It tells you how old the universe is. It tells you how fast it's expanding. It tells you whether it's accelerating or not. It tells you what the matter content of the universe is, how much of it is dark matter, how much of it is the stuff that we're made out of, how much of it is even more mysterious dark energy. And if we take that pattern, that mottled pattern that you see in the cosmic microwave background, and we look at how galaxies rotate and how the stars inside of galaxies move, if we count up in this cartoon the number of galaxies and how they evolve as a function of time to the present day, all of those paint a picture that our universe about 1 part in 6 or 7, 15% of matter in the universe is normal stuff that we're made out of, what we call baryons. The other 85% of the matter is dark matter, mysterious, don't know what it is. Someone will win the Nobel Prize when they eventually figure out exactly what it is. But the matter content of the universe is dominated by this dark matter. 15% of the matter is normal stuff. And this is bypassing dark energy, which is even more mysterious, but plays a fundamental role, as I'll show you in this cartoon. Again, this is kind of taking the same cartoon, but turning it up on its edge, with the Big Bang now at the bottom, the present day sort of, well, the present day is kind of the blue bit in the middle, and then the future going forward. There's just a few terms. I'm probably not going to use them very often, but I'll just mention them in passing. You'll hear people talk about an open universe, a flat universe, a closed universe. That's more or less a measure of the shape of the universe, the geometry of the universe. It's not particularly critical for what I'm going to be talking about, so I'm not going to belabor it very much. But it looks like, when I take all of that information that I just dumped on you in the previous slide, it looks like we live in what's called a flat universe. And if you could play God for a few minutes and draw gigantic triangles across the entire cosmos, the triangles would look like this cartoon on the right in the middle. And if you added up the angles inside the triangle, it would add up to 180 degrees. It would look like a triangle with straight edges. If we live in a open universe and we played God and drew gigantic triangles, and we added up the angles inside, it would be less than 180 degrees, kind of this sort of compressed triangle. And if it's a closed universe, the triangles look a little bit inflated, and so the angles add up to greater than 180 degrees. So again, as I talk about what is coming in the future, the difference between open, flat, and closed is not particularly critical, but if I do use the term, any of those terms, that just gives you sort of a very quick and easy way to differentiate between them. But if I come back to the cartoon, the Big Bang at the bottom, you can see this funnel opening up. This is the rapid expansion, the inflation of the universe as it's getting bigger and bigger and bigger. And if you squint and look at it just right, it looks like it's in the past. As we transition from the yellow to the orangey bits, it's starting to slow down. And if you look really carefully in the midst of that orange bits, it actually looks like it's starting to come back together again. Now, if our universe was filled with dark matter, just dark matter, and that was the only important component of the universe, dark matter feels gravity. It's an important source of gravity. And you might expect, as the universe is expanding, if there's enough gravitational material in the universe, it's going to try to pull things back together again, or at least slow down the expansion of the universe, because dark matter constrains, it pulls, because that's what gravity does. But what happens in the past 7-8 billion years ago or so, as we transition from the orangey bits into the lighter blue bits, the cyan part, is that you see, instead of continuing to slow down or even maybe close in on itself, it actually, something, somewhere, someone has put their foot down on the accelerator, and all of a sudden the universe has just taken off. There has been some sort of transition. Something has changed in the universe. You'll hear people mention things like phase transition. And it goes from being a universe where dark matter is playing its role in gravitationally slowing the universe down, the expansion of the universe, perhaps even starting to potentially pull things back together again. And then something happens. And this is where I mentioned dark energy. This is where the epoch of dark energy kickstarts. Something happens. Dark energy starts to dominate over gravity, over dark matter. And dark energy is basically, you can think of it as just being the opposite of dark matter. Instead of constraining and pulling things in, it repels, it pushes things apart. And so the universe just goes and starts exponentially expanding faster and faster and faster. And this is where we are today. We're in this phase where we can measure using the cosmic microwave background as well as other probes. We're in a phase where dark energy completely dominates over the dark matter, and the universe is not just expanding, as we showed when we were using the Hubble Space Telescope to measure the present day expansion rate, it's actually accelerating. So if we could come back in the future, a few billion years, we would measure a different Hubble constant because the universe would be expanding even more rapidly than it is today. And we have, again, multiple lines of observations which show this. This expansion is accelerating. It doesn't necessarily tell you whether it's going to accelerate forever and ever and ever. To foreshadow where it's coming, that's probably what is going to happen. And there's going to be a lot of interesting things that will happen between where we sit today in kind of the middle of the plot and wherever this plot may end at the top. And that's what we're going to be doing over the next few minutes. To give you a few important points in the timeline from the past to today, not just sort of the cosmic, the Big Bang and the cosmic microwave background appearing sort of 13.5 billion years ago. Again, just a few numbers to bear in mind as we start leaping forward in time. The bulk of the Milky Way, there's not one point where you say the Milky Way formed at exactly this time, or the Andromeda Galaxy formed at exactly this time. So if it formed, the bulk of those galaxies formed over, period between 9 and 13 billion years ago. It's still forming today. We are still accreting and cannibalizing our neighbors like the Magellanic Clouds and the Sagittarius Dwarf Galaxy. So we have not finished the formation phase of the galaxy, but the bulk of it formed, 10, 12, 13 billion years ago. If you look at our solar system, again, we typically we say the sun is what, 4.5 billion years old, whatever the number is. But there's a process. It takes time for the solar system to form. And it formed over that period of time, 4.5, 5.5 billion years ago, where that protostellar cloud led to the formation of a protoplanetary disk and time for the planets to form. So that sets you a timeline 5-6 billion years ago. If we now look at, say, life and the timeline over which life has appeared, it doesn't appear instantaneously. Planets are pretty hostile environments when they first begin to form. So it takes time for things to settle down and stabilize. At least on planet Earth, it took about 1 billion years for life to first appear. So about 3.5 billion years ago. Took about another 1 billion years for multicellular life to appear. When you start to get to more quote unquote advanced life forms, it really is a tiny little snippet of time compared to the full timeline that we've just been discussing thus far, with mammals only appearing in the last sort of 200 million years or so, and Homo sapiens only in the last 200,000 years or so. So before you sort of project forward and look at the ultimate demise of the universe, it's also important to just keep these numbers in mind, because the numbers are going to start to grow exponentially as I start going forward in time. And it's also worth reflecting on just how lucky it is that, we've made it this far and we're still able to sit here tonight and actually have this conversation, because there's a lot of astrophysical things that we've had to navigate in order to survive, for Homo sapiens to appear 200,000 years ago, for mammals to appear 200 million years ago. So just a reminder of some of the things that we have navigated thus far, because again, these will come forward. They will become increasingly important as we leap forward in time as well. So there's lots and lots of ways in which we could have been decimated or wiped out so that we would never actually have this conversation. You could have an entire talk about the ways in which you can perish through societal, socio-political effects, mutual self-destruction, pandemics, whatever the case may be. There's lots of ways that you could wipe yourself out on this timeline. And we've come close on multiple occasions, but these are topics that are, for another day and really do cross into the socio-political side of things. But if you look at just the astrophysical things that we've managed to navigate, I'm not going to touch on every single one of them, but there's a couple of them that are important because they have happened in the past and they will happen again in the future. Now, if we could step outside and look down on our Milky Way galaxy, it would look kind of like this cartoon over here, a grand design spiral arm, a bar cutting across the center, and the spiral arms coming off the edge of the bars, and there's various spurs and lots of other little things happening there. But it's a beautiful, elegant, classical, grand design spiral, 100 billion stars or so, plus or minus. And then this picture here, they're all going around the galaxy at roughly the same speed in nice circular orbits, all going roughly 500,000 miles per hour, whether you're in the inner part of the disk or the outer part of the disk. We're all moving at roughly 500,000 miles an hour as we go around. And we sit in between two strong spiral arms on a little spur. And that's potentially quite important for us in the sense that there's not much around us right now. And there hasn't been much around us for the last 100 million years or so. We've got some stars that are nearby, Proxima, Alpha Centauri. But in the grand scheme of things, we're in a pretty empty region of space between the spiral arms. Most of the action in the galaxy is tied to these spiral arms. There's 10 times the amount of stuff, gas and dust and stars, all the newborn stars that are forming. They're all attached to the spiral arms. There's just not a whole lot around us right now. So that's probably an important component in the development of life, in the sense that nothing really bothers us. Now, where we sit, we move at almost the same speed as the spiral arms as we circle our way around the galaxy, but we don't move at exactly the same speed. So every few 100 million years or so, we actually catch up to the spiral arm in front of us, and we go from a region where there's not much around us to a region where there is a lot of stuff around us. And it's a bad analogy, but you can, when you're driving in the car, there's air inside the car, there's air outside the car, you stick your hand out and you feel a shock as the wind presses against your hand. Now, as we move from a region between the spiral arms to a region where there's not much around us into the spiral arms where there is a lot of stuff around us, it's not a wind that you feel, but it's actually a shock due to gravity, because there's not much around us right now. We move into the spiral arms where there is a lot around us. So instead of getting jostled by wind, you actually get jostled by gravity as you go from low dense region to high dense region. And this happens every few 100 million years or so. And, if you look at our solar system, the planets of our solar system, as they move around the sun, the only gravity that they care about is the sun. The sun dominates the gravity of the inner part of the solar system. So as we move through spiral arms, it doesn't really affect the planets at all, because again, the sun's gravity completely dominates over any extra gravitational effect of the spiral arms. What it does affect, though, is the outer part of the solar system. So on the top panel there, the little circles are different planets. But if you could zoom out of our solar system and look at it from further afield, not that you can, poor color choice, but our solar system that we know and love in terms of the planets is a tiny little blue box right down in the center of this. We're surrounded by this Oort cloud of billions, possibly trillions of comets. They're also held onto our solar system by gravity, but they're held on very, very loosely. It doesn't take much to jostle them and shake them loose. And going through a spiral arm does, kind of ring the bell of the solar system and shakes up not the inner part of the solar system, but shakes up that outer part of the solar system where all of those comets are sitting. And when that happens, a lot of those comets will get shaken loose and fly away, and that's fine. But a fair number of them will get shaken loose and come raining down to the inner part of the solar system. And, this does happen. If we go back, the last time this really happened in a major sense was when one of these comets came into the inner part of the solar system and impacted on the Earth about 65 million years ago, and wiped out something between 70–80% of the species that existed on Earth at the time. Now, we're still here to have this conversation tonight, so clearly it did not wipe out all life. Now, if you were to interview the dinosaurs, they would say this was a very bad thing because it took them out along with the other species. So these things do happen. We're a bit fortunate that we weren't entirely decimated. But these things do happen, and that killer comet, if you like, was somewhere like between 10, 20, 30 miles or so in diameter. That's the sort of thing that is a species killer, that takes out a significant fraction of the number of the species that might exist on the planet at any given time. So these things do happen, and it's not just our planet that feels this. Many of you will remember, as I do, in the mid-90s when Comet Shoemaker-Levy broke up on the surface, if you like, the outer atmosphere of Jupiter, and left its debris scattered across. Now, I had to write down the diameter, the size of Shoemaker-Levy was about a mile or so in diameter. So 10, 20, 30 times smaller in size than the species killer, but still would have caused an enormous amount of damage if it had impacted on Earth. Now, we're fortunate, we've got Jupiter outside of us, the outer, the mid to outer part of the solar system. It really acts like a gigantic gravitational Hoover. And so obviously some comets do make it right down into the inner part of the solar system, but we have this partial gravitational shield that helps hoover up some of these comets before they ever make it into the inner part of the solar system. And there's much debate as to how important having this gravitational shield is, but it is probably one piece of the puzzle that allows life to develop, that we have this extra level of protection in the form of Jupiter to hoover up these sorts of things. For comparison, if you take the Tunguska event in the early 1900s, the size of that was about a football field across, about 100 meters or so. So much smaller than Shoemaker-Levy, and much smaller than what took out the dinosaurs 65 million years ago. And for comparison, the biggest event in recent memory was the Chelyabinsk meteorite, which is a meteor which you can see here. Lots of spectacular dash cam images of this thing coming down in Russia. Lots of damage, many hundreds, thousands of people injured from this particular strike. There's lots, you can just YouTube it. There's an enormous, lots and lots of videos of what happens when something like this impacts. And that one was only 15 meters or so in size. So significantly smaller than Tunguska, significantly smaller than Shoemaker-Levy, way smaller than the one that took out the dinosaurs. But these things happen. I'm actually holding right in my hand right now is a chunk of the Chelyabinsk meteorite, which cost a lot more than I would like to actually say here publicly, but one of our recent purchases that we're really proud of. So there's lots of ways that you can die. One more before we start moving forward in time is coming back to this cartoon of our Milky Way galaxy. As we move into the spiral arms every few hundred million years or so, we get this gravitational shock that I just talked about. But that's also where most of the stars in the galaxy are forming. And big stars that are 10, 20, 50 times heavier than the sun, that's where they're forming. They live fast, they die young, and they die spectacularly in the form of a supernova, which is what the little animation which is running on the side there. Now, these things are great because basically everything, as you look around the room you're sitting in right now, started its life in one of these types of exploding stars, 7, 8, 10, 12 billion years ago. Everything heavier than hydrogen, helium, all the other chemical elements, the iron, the carbon, the nitrogen, the sulfur, magnesium, silicon, et cetera, everything that is fundamentally important to our life and our planets and our solar system formed in these sorts of things. So that's the positive. The downside is they're incredibly powerful, billion times more powerful than the most powerful nuclear weapon that's ever been exploded on Earth. And much like a nuclear weapon, if it explodes on the other side of the Earth, we don't feel the impact of it here, sitting in the UK. But if it, explodes in the town next to you, it's obviously going to have a big effect. Same thing happens with supernova. A supernova, an exploding star in our galaxy, it goes off maybe once every 10 years or so. One explodes. So we've had about 1 billion of these events over the lifetime of the galaxy, but the galaxy is really big, so most of them are far away from us. And there's, again, much debate in the community as to how close you can be to an exploding star before it actually completely destroys and evaporates your biosphere. the best guess right now is a number around 20 light years away from us. If you're closer than that, when one explodes, that's going to wipe out your biosphere. If you're outside of that lethal radius zone of a supernova, yes, it can do a little bit of damage depending on how close it is, but your biosphere is likely to survive. So not only do you have to worry about being shaken up by the gravitational shock, you do have to be a little bit worried every few 100 million years of being too close to an exploding star as you pass through the spiral arm. And these sorts of things, do actually happen. The last one was about 10 million years ago, when we just happened to coincidentally be close to a star that exploded. Now, that one was about 100 light years away from us, so it's outside of the 20 light year lethal radius. So it was far enough away that it didn't destroy our biosphere, but it was close enough that it left a very thin layer of a radioactive isotope of iron called iron-60, only formed in exploding stars. There's this beautiful thin layer left all the way across planet Earth as the shock wave of the exploding star swept over us, and it left this radioactive isotope covering the planet Earth. This thin layer of it has a 2 million year half-life. And so we're able to observe that iron-60 today, and we can trace it back to exactly when this shock wave washed over planet Earth. So we were uncomfortably close to that lethal radius zone of 20 light years. Again, we're still here. We've been lucky. We've navigated these various events that have come along and wiped out species, or have become perilously close to being able to wipe out our biosphere, like the exploding star 10 million years ago. But again, the glass half full side of this is that we're still here to have the conversation. So there are lots of astrophysical things that can take you out, but we're still here. So that is the positive way to view this. So now what I'm going to do is we're going to start moving forward in time and look at some of the things that could take us out before we ever get to the point of having the conversation about the ultimate fate of the universe. I think it is sort of important to look at some of the things we do need to navigate before we actually reach that point in time. And what is the universe going to look like as we move forward in time? So I'm not going to touch on absolutely everything that's going to happen between now and the end of the universe, but I picked out a few interesting signposts along the way. So the first one I picked out is 10,000 years from now. This is Antares. It's a star that's about 15 times the mass of the sun. It is, I think, the 16th brightest star in our night sky. It's very difficult to observe. If you get up at the crack of dawn nowadays and look well down in the south, it'd be a few degrees above the horizon. The best guess is this is one of the nearby stars that is going to explode on that sort of time scale of thousands of years. But it is 600 light years away, so we're well outside that 20 light year lethal radius zone. So we're safe in that sense. But it will be, if you are around in 10,000 years, it'll be spectacular. Outside of the sun and the moon, it'll be the brightest thing in the sky. It'll be brighter than Venus and Jupiter. It will be easily visible in daylight. So that's something to put in your calendar for 10,000 years from now. If not for yourself, then your great grandkids. If we go forward 300,000 years from now, this is another star. This is about 30 times the mass of the sun. It doesn't have a particularly exotic name. It's what we call a Wolf-Rayet star. WR104 is its name. Now it's 7,000 light years away. There's some prediction that it's going to explode on that sort of time scale, 300,000 years, plus or minus. 7,000 light years away. So again, it's way outside the normal lethal radius zone. But this one is a little bit more different. It's got a lot of attention in the community, largely because it's rotating really, really fast. And stars that rotate really, really fast, when they explode, there is a statistical chance that it won't be just a normal supernova, which is already crazy energetic, but it might be something called a gamma ray burst. So there's been a lot of debate around this particular star as to whether this is going to be one of these gamma ray bursts that when they explode are 100 times more powerful. And more than just being 100 times more powerful, they take all of that enormous amount of energy and they focus it into these jets that come out of the, if you like, the north and the south pole of this rotating star, which is about 30 times heavier than the sun. So it's an incredible amount of energy, but it's also focused in these incredibly tight beams. Now, if you're near a gamma ray burst, but you're off to the side, you know, it's okay. No worse than a normal exploding star. But if you happen to be in the path of the jet, that's not so good. And this star has got a lot of attention. And if you can go back to press releases from a few years ago, when groups suggested that the pole of this rotating star was actually pointed straight at us, or close enough to us that when this thing exploded, there was the potential, and the prediction was made that the jet would be pointed right at us, like a barrel of a gun. And if that were to happen, that would be, even though it's 7,000 light years away, when you focus all that energy into one beam and point it at you, that would be enough to evaporate our biosphere. 300,000 years, that's not very far in time. That's roughly how long that Homo sapiens have been around here on Earth to remember. So it's a very brief period of time in the grand scheme of things. Now, over the last couple of years, people have been studying this star over and over and over again. The initial claim that it was pointed straight at us, the pole, seems that people have backed off from that now. It's a really difficult measurement to make. And so what people now look at this star, and they still think it's going to explode as a gamma ray burst, but we don't have a clear picture as to where it's going to be pointing. So you can play the game and say, let's just say the jet comes out in any random direction. What is the likelihood that enough of that energy will be pointed at us that could wipe out our biosphere? And the best guess is that if we lie within 12 degrees of this thing pointed straight at us, that would be enough to wipe out the biosphere. And so you can play the game and say, well, what are the odds of that just randomly happening? It's about 7%. So it's a 1 in 14 chance that this star, when it explodes 300,000 years from now, will wipe out our biosphere. So again, it depends on your glass half full, glass half empty. So your half full optimistic is that you've got a 93% chance that this is not going to wipe out our biosphere. If you like the glass half empty side of things, then you've got a 7% chance that this is going to wipe us out 300,000 years from now. Again, very brief snippet of time in the timeline of the universe. It has been suggested that an event such as this might have been responsible for the even greater mass extinction event that occurred in the late Ordovician, so 450 million years ago or so. I don't think that's probably really the case, but there are some papers out there that suggest that perhaps that was the case. Again, I suspect that is not going to stand up to the test of time. In the same way that the Cretaceous Tertiary one, we really know that was due to an impact event. The Ordovician one is probably not an astrophysical event, despite a handful of scientists claiming that maybe it was. If we go forward 1 million years from now, this is when things start to get a little bit more interesting. We're not going to pass through the spiral arms for another 100 million years or so from now. But I mentioned right near the beginning, we've got 100 billion stars in the galaxy. They're all moving at 500,000 miles an hour in nice circular orbits going around the galaxy. But not every single one of them is moving in lockstep in a nice circular orbit around the galaxy. Things come along that bump stars gravitationally and change their orbit a little bit. And so this is one star called Gliese 710. It's 60 light years from us right now. But this star, I can't remember, it's about 10th magnitude. No, I didn't write it down. About 10th magnitude or so. Looks like any other star in the sky, but it's different in the sense that it is coming straight towards us. It is like, again, a barrel of a gun pointed right at us. And in 1 million years, this star is going to pass right through our solar system, not quite down in the center of the solar system where the planets are, but it's going to move right through the Oort cloud in the outer part of the solar system. And this star is maybe half the mass of the sun, but its gravity will be enough to shake loose an enormous number. Tens of millions of comets will get shaken loose from the Oort cloud when this happens in 1 million years from now. And, the hope is that, the vast majority of them will miss us. Now, this is this bit of a busy plot, but I think it's a really important one because it's one of the more exciting, to me, results from the last few years that we stumbled across. Along the horizontal is time. 0 means today. The negative numbers to the left mean going back in time. Positive numbers to the right is going forward in time. And we've taken maybe 50 stars that are near us right now, and we've been able to figure out how those stars are moving. And we can look back in time and see what is the closest any of the nearby stars have been to us, or we can go forward in time and work out the closest any star is going to be to us on the time scale of millions of years. And as you can see, most of the stars are more than what we call 1 parsec. So for context, these sort of distances here are, the distances like to Proxima and Alpha Centauri. And nothing gets really close to us in the past or in the future, except for the 1 circle that I've drawn there, which is the star that I've just described, Gliese 710. It is going to basically run right through us. And the best guess, and it's impossible to predict it, is it will shake loose something like about 10 million comets or so that will come. And that's just the ones that will come raining down to the inner part of the solar system. And again, best guess is something on the order of a naked eye comet will appear every month for the next 1 million years after this star passes through our solar system. So again, all it takes is just one of those comets to make it past Jupiter and be of a size similar to the one that took out the dinosaurs at 10, 20, 30, 40 miles across in size. That's the sort of thing that could take us out. So if I was to put hand on heart and guess what is the astrophysical thing that might wipe out planet Earth or our biosphere well before we ever reach the end of the universe, it's going to be this thing in 1 million years when we have a sky filled with comets raining down to the inner part of the solar system. So if you like observing comets, it's going to be spectacular. It's going to be great. Hopefully we'll have the technology by that point in time to be able to deflect them from ever coming in hitting us. But this is something to look out for in 1 million years time or so. Now I'm going to race forward over the next sort of 10 minutes to leaping forward in time in bigger and bigger chunks. I'm going to move from 1 million years in the future to 100 million years from now. And as I've said, while we can point to the event that I just pointed to, we can pinpoint to happening in 1 million years. These sorts of potential mass extinction events come about every sort of 100 million years, few 100 million years or so. So statistically, this sort of mass extinction event will occur. It may not be exactly in 100 million years from now, it may not be exactly 200 million years from now, but we do pass through spiral arms. We do have our Oort clouds shaken. We do get those comets come raining down on us. So there is a statistical game that we're up against. Again, we're still here today, so that is the positive to take from that. But it is something that one is always facing on that time scale of a few 100 million years. These statistics may catch up with you. And you might ask, say in a few 100 million years, what's Earth going to look like? Let's say none of these things wipe us out. What is Earth actually going to look like? Well, it's going to look really, really different than it does today. The moon will have drifted a little bit further away from us. It'll be about 6,000 miles further away, which doesn't sound like a lot in the grand scheme of things, but it does mean our day will go from 24 hours to 25 hours in duration. So that's kind of cool. We will have completed our 20th lap around the Milky Way. But the real thing that, if you're sitting here on Earth to notice is that the Earth will look really, really different. That's because all of the tectonic plates that we're sitting on, they're all moving around. After 50 million years, I'm up to 100 million years in this animation now, but it only took 50 million years before Australia, because it is moving so fast, plows into Southeast Asia. You can see the Antarctic moving its way up. It takes a couple 100 million years before it reaches South America and Africa. But after a couple 250 million years, rather than having the current set of continents that we have, we'll be left with basically one mega continent kind of moving, straddling the equator, the mid part of the Earth. So Earth will look very, very different in the sort of timescales that we're talking about, of having passed through 1 or 2 spiral arms, And so you can have a really interesting talk just about this particular animation and how fast Australia is moving. It is so much faster than any other continent. It's moving, to write it down, it's about every 10 years it moves about a meter or so, or if you like 3 inches per year, which again doesn't sound like a lot, but it is so fast that the normal sat nav, Google Maps, GPS that we take for granted here doesn't work when you're in Australia. So Australia, you have to make all kinds of extra corrections to allow Google Maps and sat nav to actually work because it is moving so fast. So the Earth will look very, very different if we are around in 250 million years. On roughly the sort of the same time scale, a few hundred million years or so, Earth is going to be more or less just not going to be really, it's going to be so inhospitable. You're not going to really be able to live on planet Earth. And that's because the sun is evolving. In 500 million years from now, it will be 1 part in 20 brighter than it is now, which doesn't sound like very much. It's only 5%, but that's enough to drive sort of a moist greenhouse effect. We start evaporating the oceans more efficiently. And this is independent of anything that we're doing to ourselves through our own mutually assured destruction. Stellar evolution eventually catches up with you on that sort of time scale. So the average temperature of the Earth in a few hundred million years will be 50 degrees centigrade. You might think, well, I can move to the poles, but there isn't really any poles anymore because we've got this one mega continent around the equator. You could have some sort of water world existence, maybe living up in the poles. But we'd have to be, if we're still here on planet Earth in that period of time, you'll have to be subterranean or living underwater or something like that, because the surface will just be unlivable. And by the time you get to 1 billion years or so, the average temperature on the Earth is almost at the boiling point of water, 80 degrees centigrade. So on that sort of time, and again, 500 million years is not that long. That's only, not much longer than mammals have been around on Earth. So again, a very short period of time in the grand scheme of the timeline of the universe. Earth will be inhospitable, at least on its surface or so. So we'll have to be a radical rethink as to how we're going to live. And you can also play the statistics game as to when a gamma ray burst might be pointed towards us. And again, whether it's 500 million years, 1 billion years from now, you are playing this statistical game that eventually you will have a gamma ray burst that might go off and be pointed towards us within the lethal pointing angle of where these jets actually point. And Earth will look very, very different as well in this sort of time scale, because you'll have, the moon will have drifted so far away. Weird things like you won't have total solar eclipses anymore. It'll be a bit sad. You still have like coronal eclipses, but you won't have the total solar eclipse anymore because the moon will have drifted far enough away. If we leap forward even faster to 3 billion years from now, the night sky is going to look radically different. The moon will be about a quarter further away than it is right now, 75,000 miles further away than it is. And now that's, again, is really important because the moon keeps the Earth stable. We're tilted, as you probably know, what's called the obliquity. We're tilted 23 degrees away from the sun, but we stay nice and stable as we go around the sun year by year by year, because the moon acts as a really strong stabilizing anchor. It's, again, probably part and parcel of the importance of the development of life. The sun in this time period of time will be 40% more luminous. It'll be, average temperature on the Earth will be a few hundred degrees centigrade. It'll be approaching the point where it melts rock. So there's nowhere on Earth you'll be able to live, at least on the surface, on that period of time. But the sky is also going to look very, very different, because while all this is going on, our nearest neighbor, Andromeda, is moving towards us at, I have to write down what the number is, something like, how fast is it moving towards us? About 250,000 miles per hour. So in a few billion years from now, the Milky Way and Andromeda will actually collide. They interact initially, they feel each other's gravity, they get pulled together, and eventually they merge, leaving behind a single new galaxy, probably call it a giant elliptical. So the big, beautiful Milky Way will be gone. We won't see that lovely band cutting across the sky any longer. Now, again, the galaxies are mostly empty space, so stars aren't likely to actually run into each other. But the ultimate output of this interaction 4 or 5 billion years from now is a single giant elliptical galaxy. So the sky will look very, very different at that point in time if we are still around. Not too much longer after that, the sun runs out of its fuel. It stops burning hydrogen into helium. It becomes what we call a red giant, kind of like Betelgeuse. Bloats up its outer atmosphere. That will incinerate the Earth. Mars might be a nice place at that point in time when we become a red giant. So that buys you maybe a couple billion years or so during a red giant phase, where Mars becomes a lot nicer, but Earth will be incinerated during that phase. And if you go forward a few billion years further in time, then any residual heat from the sun is gone, and what's left behind is the remnant called a white dwarf, likely to crystallize into something, basically a gigantic diamond, an Earth-sized diamond, worth, I mean, the numbers are meaningless, they're a crazy billion, trillion pounds, so a billion times the Earth's gross domestic product. So if Elon Musk is still around at that point in time, there'll be an enormous amount of value tied up in this Earth-sized diamond, which is the remnant of the sun. And that white dwarf is the remnant of all stars like the sun, stars up to 5, 6, 7 times the mass of the sun, and their lives with these sorts of white dwarfs. Now we're gonna, in the last few minutes, is really race forward in time. If we leap forward 100 billion years from now, if somehow Earth was still around, maybe someone was able to push the Earth's orbit out a bit further so it survived being decimated by the red giant phase, the Earth's core will have cooled enormously. Now we have the benefit of having a hot, turbulent iron molten core, and it's critically important for the development of life because it is responsible for the generation of the magnetic field that protects us and that allows life to develop. And again, this is part of the important ingredients probably for the development of life, is having a magnetic field. It's not the most important, but it is one piece of the puzzle alongside some of the others that I mentioned. The Earth's core will have cooled sufficiently in 100 billion years from now that magnetic field will turn off. Surface radiation, if there was the sun was still around, would increase by a factor of 10,000 or so. And that's the equivalent of getting a full body CT scan, every couple days or so. If you're an observer, it's going to be very different. If you use the Hubble Space Telescope today and take a deep image of the sky, like this ultra deep image, it's spectacular. You feel what you're seeing there is almost everything is a galaxy there rather than a star. If you did the exact same observational data, observation in 100 billion years from now, this is what the sky would look like. It's not quite as exciting. There's a few little blips in there, which are things like the remnants of like white dwarfs that I've just talked about. There's actually no galaxies to be seen. And the reason is the universe, like I said right at the very beginning, it's accelerated. It's continuing to accelerate. Nothing has been put forward to stop that. And so everything is flying away from each other. And so all of the galaxies move beyond what's called the cosmic light horizon. And I'll just take 1 minute because this is sort of an important concept. Here's us in the center. We can look back in time 13.5 billion years in any direction. It's the age of the universe and the speed of light. So our light horizon, in this direction, we can see this galaxy 13.5 billion years ago. We can look over at this galaxy on the right, and it's still within our light horizon, 13.5 billion years look back time. Now, for someone over who's sitting in that galaxy on the left, they can see us because we're within their light horizon, but they can't see the galaxy over here on the far right because it's outside of their light horizon. And so this is something that we will everyone, whichever galaxy you're living in, has to face in 100 billion years. Everything is rapidly moving and accelerating away from each other, and galaxies disappear beyond the cosmic light horizon. And so in 100 billion years from now, we will not see any other galaxies at all. The night sky will be very dim with just a few remnant stars like white dwarfs that are cooling that you can actually observe. So if you're an extragalactic astronomer in 100 billion years from now, it's going to be just awful because there's not much for you to do observationally. You'll have to do just theoretical work. 1,000 billion years from now, all the gas in the universe that's left over inside of galaxies will have been used up. So there's no more stars to form. You know, when we form a star like the sun, when it dies, it's, you know, half of it stays in a white dwarf, half of it gets returned. And then that gas gets incorporated into the next generation of stars, which locks up material into remnants, returning just a little bit. So as you go forward in time, you're progressively using up gas and locking it into remnants. So 1,000 billion years from now, there's no more gas. That means no more stars are going to be formed. 100,000 billion years from now, the last of those shining stars extinguished, so there's no more starlight at all. So the only thing that is left are these crystalline white dwarfs that have cooled down to basically diamonds and are giving off no energy whatsoever. And neutron stars and black holes, the remnants of stars that are much heavier than the sun, when they explode, leave behind neutron stars and black holes. So there's nothing to see if you're an optical astronomer, just these crystalline white dwarfs, neutron stars, and black holes. You leap forward 100 billion years from now, and those remnants, the vast majority of them, 99% of those white dwarfs and black holes and neutron stars, get tossed out of galaxies because enough time passes that occasionally two black holes, or a black hole and a neutron star, will come close to each other. And one of them, which is a little bit lighter than the other one, will get a slingshot effect and get, you know, they'll pass by each other, it'll gain a bit of energy and go flying away. And so the vast majority of these remnants will get tossed out of the galaxy, leaving only, and this is something called two-body scattering, the 1% that don't will fall into the supermassive black hole that is sitting at the center of the Milky Way. This is a beautiful work that was done by the group at UCLA in the US, for which the team was awarded the Nobel Prize in Physics last year, determining the mass of the supermassive black hole at the center of the galaxy. So again, in 1,000 billion years, all that's left of our galaxy is this single supermassive black hole. All the other little ones have gotten tossed out of the galaxy, out into the cosmos. And if you go forward even further in time, billion years, the protons, the neutrons, the fundamental particles that form these remnants will actually decay. So neutron stars will decay, the white dwarfs will decay. The only celestial objects that are left are black holes. Those haven't decayed yet. Everything else, all the neutron stars, white dwarfs, any other remnant that's left over has decayed, giving up. You know, protons and neutrons are gone. You give off a little bit of energy and you create something kind of like an electron, but a positive charge, called a positron. And now the numbers become crazy, billion. You can read off all the billions of years there. The only thing that's left at that point are these black holes, but even black holes are not there forever. They will decay. This is one of Stephen Hawking's beautiful work, giving off what's called Hawking radiation. And you can think of this as, you can have, you know, what's labeled number one here. You can have virtual particles that can appear almost out of the ether, vacuum fluctuations. A positive, this is allowed by quantum mechanics. So a positive and a negative charge appears, and then they can disappear really, really quickly according to quantum mechanics. And if they happen far away from the black hole, they come, they go, you're basically blissfully unaware of it. If they appear near the event horizon, they form, they kind of steal energy a little bit, gravitational energy from the black hole, and they form a particle and an antiparticle. So you've stolen a little bit of mass energy from the black hole to form this virtual particle, but they fall, in this case, particle 2, they both fall back into the black hole. So you've stolen a bit of energy to form the virtual particles, but they fell back in. So the net effect on the black hole is nothing. But you have this case here, situation 3, where you form a particle and an antiparticle, stealing a little bit of gravitational energy from the black hole to form it. And one of the particles falls in, so it gives back its mass or its energy to the black hole, but one of them has escaped. And so when this happens enough, you slowly evaporate the black hole in an enormously long period of time by stealing a little bit of gravitational energy to form these virtual particles. And some of them escape, which means you're stealing energy and you're slowly evaporating the black hole. It takes a crazy long period of time, but that's what you end up with at the end. And so the only thing left at this point in time, these many crazy billions and billions and billions of years, is this dilute gas, and all the while the universe is expanding and accelerating and like crazy. The only thing that's left is a little bit of energy, photons, and some of these, what we call leptons, electrons and positrons. The universe is expanding, accelerating still at this point in time. These photons and leptons are cooling and cooling and cooling to increasingly low energy levels on, again, crazy long time scales. And this is what the final state of the universe is. It's called the heat death of the universe. There is nothing left except these photons and effectively electrons, leptons. It reaches what we call thermodynamic equilibrium, all the while continuing to expand forever. There is nothing the universe can do to create anything more. There is nothing left. And so that's the way the universe ends. It's not with a bang. It's nothing spectacular, but it's this slow, painfully slow whimper to the end of the universe. Now, the way I like to end on a positive note is that, trying to address the topics that we've been talking about tonight and answering the questions associated with the end of the universe and the evaporation of black holes, all of that sort of analysis and scientific research has led to inventions like the World Wide Web and Wi-Fi. We wouldn't have those things today if people were not trying to answer these questions. So again, it's a topic of an entirely different talk, looking at what are some of the important contributions that astronomy has made to society. So we don't often think of, the study of black holes or the early universe or the ultimate fate of the universe as having some anchor in the real world in our day-to-day lives. I've alluded to a couple of them right now with things like GPS and sat-nav, but again, things that we're using, right now, most of us are all attached to, using Wi-Fi right at this moment in time. Wi-Fi was an invention of astronomers who were trying to prove the existence of primordial black holes that Stephen Hawking had postulated existed. So that is again, a glass half full take on the talk, is that these sorts of inventions have come around from trying to answer the broader scientific topic that we've been talking about tonight. So I don't have any fancy summary other than just noting that depending on your take, the future can be depressing, can be scary, it could be lonely, but the universe does look like, from everything we can tell right now, that it's going to end with this whimper and not with a bang. And I think that's everything I wanted to say. Thank you for listening. I do want to just give you an advertisement for something that's coming up. You're not going to be able to read this, but you're recording it so you can go back and look. Pint of Science is a kind of a worldwide outreach event that's normally held in pubs and bars, and it tries to capture the essence of, the conversation you might have over a pint in the pub. It's being run, unfortunately, still virtually this year, but hopefully next year it'll be in real life. But we've got a really exciting one that is being driven by 4 of the students that I talked about at the very beginning, who will be exploring in a series of 10-minute talks, everything from the origin of the chemical elements to the origin of galactic halos, with my student Leah, and Emily, who is from Mansfield, where many of you are sitting. We'll be talking about large-scale structure and the cosmic web, and it'll all be hosted by one of our students, Kiri Newson. So I'm trying to promote this because it's a great opportunity to really hear from the next generation of women in physics who are really taking a leading role in widening participation and diversity. So it's a really exciting event. It's free. Just go to Pint of Science and hunt around and you'll find it. So set aside an hour at 7 o'clock on May 19th to come along and hear from the next generation of scientific leaders. And thank you yet again.